This Master of Science, Political Ecology. Never heard about it, political ecology, but maybe it's interesting. In Michigan State, and then after that, it's PhD in Berkeley.
That works.
And then moved to University of California, first as assistant professor, and now since 2019 as associate professor. And her topics are soil sciences, especially the effect of changing environment, and some of the achievements are New Voice in Science Award by the United States National Academy of Science. So congratulations to that. So, and the floor is yours, please.
Thank you. Good afternoon, everybody. I'm really glad that I'm actually finally here. There was a chance this morning that looked like I might not actually be here right now, so I'm really glad that is not the case. Thank you for the invitation. I really appreciate it. I'm a soil scientist, as you heard, and I'm decided I would tell you a little bit about the work that I do in general that we do in my field, and a couple of important, at least the ones I think important tidbits about me as a woman and in the sciences. Okay, so as I said, I'll start by talking a little bit about me and then talk about the work. And briefly near the end mention a couple of points that I think are very, very important, in particular in the endeavor of trying to bring women and girls in sciences, not just to increase interest, but also to make sure that when women and girls do actually enter science, that they're actually to have a safe, inclusive, and equitable workspaces. Is this working? Okay, I feel, okay. Okay, so let's start with who am I? A lot of things, I guess you could say. Probably my most cherished roles are I'm a mom, two beautiful kids that you see in the middle right there. I'm also married to another soil scientist and academic. So obviously I see that as being one of the most important defining kind of qualities of who I am. I'm also a daughter, obviously, and a professor and a scientist and somebody who's really passionate about this topic of women and girls in science, and also underrepresented minoritized scholars. So people from underrepresented backgrounds, be it by race, gender, sexuality, geographic origin, income levels, and everything else. Make sure that we have a level playing field in science. I was born and raised in East Africa, in Eritrea, but right now I've lived half my life in the US, so virtually my entire adult life has been in the US, but I was born in Eritrea, so I guess you could say I identify as Eritrean American or Eritrean American, if you prefer the hyphen versions of it. Okay. So as in my science work though, so a lot of the work that I do is motivated by trying to get an improved understanding of what controls the biogeochemical cycles of essential elements such as carbon and nitrogen. But I'm also highly kind of engaged and think a lot about contemporary concerns about issues around soil health and soil security. And I'll tell you a lot more about soil health going forward. What I mean by the first point is, you know, we've known for centuries at this point that the type of soil that you have around the world and the properties of soil are governed by these 5 factors that we know, that we refer to as state factors of soil formation, that include climate, biota, parent material, or the rock that you start with, relief or topography, and then how long the soil has been forming. In my group in particular, we spend a lot of time thinking about climate variables and how they regulate biogeochemical cycles of essential elements, but in particular climate change and how things are happening in that space. We also think about how geomorphology intersects with biogeochemistry to affect these cycling of biogeochemical cycles of essential elements. And what I mean by security, in case this term is new to some of you, is this idea that human life and sustainability of the resources that we depend on in the 21st century are increasingly coming under threat. And the idea here is that even though our survival depends on these earth resources, including soil, these resources continue to get degraded because of human actions. And so in the 21st century, we're not even going any further than this next 100 years, basically, that human life and success is going to have to depend quite significantly on how well we manage our resources and whether we're willing to reverse the path that we're on that has been very, very destructive from a resource perspective or not. Just to give you a tiny bit more specific, so in my group then, I'm fortunate enough to work with a dynamic group of students, postdocs, and other researchers to ask questions specifically about what happens to these biogeochemical cycles of carbon, nitrogen, and including phosphorus, when things like physical change in the environment happen, things that include erosion, fires. I'm in California. There's a lot of fires, especially lately, right? And also then these climate change variables or global change variables, including change in atmospheric temperature or change in amount and distribution of precipitation that is happening around the world right now. So we ask questions then, how do these forcings affect processes within the soil system that have to do with their rate of cycling, their vertical and lateral redistribution in the earth system, and does that matter for how we retain resources? But also the fundamental chemistry that happens at the nano or molecular scale, because keep in mind that a lot of minerals in soil, in particular the reactive minerals that play very important roles in regulating carbon and nitrogen and phosphorus cycling, are naturally in the nano-sized. And these minerals then tend to be very, very reactive and have, so we spend a lot of time thinking about the fundamental chemistry at that level. And then the other part is this sustainable use of resources, and in particular the soil-societal relationships that we think about. So when I talk about biogeochemical cycles of essential elements, essentially what we're focusing on, a lot of the work that we do focuses on what we refer to as soil organic matter. And if you know anything about soil, you know that big portion of the soil is made out of mineral matter, right? Something, like 5, maybe 20% under rare cases is made out of organic matter, which is basically made out of a collection of residue of living things that used to live in or around the soil at one point or another, and are decomposing basically over time. And we spend, people like me and Wolf right here, we spend a big chunk of our careers focusing on that relatively small proportion of soil that is organic matter. But there's a really good reason why we do so, right? Because that is really central to regulating life in soil. To start with, this organic matter serves as the food and energy source for living things, and hence why we care a lot about it. It also regulates physical stability of soil and its resistance to erosion, because it allows the soil to form aggregates that are able to stabilize it. And organic matter also tends to be very reactive and plays major roles in the chemical reactions that take place in soil, including ones that regulate provision of essential nutrients for plants. So fertility, ability of that soil to provide plant essential nutrients, and ability of soil to resist sudden changes that could happen with environmental change, for example. Okay. That's enough about background in my lab, and and we'll talk a bit more about generally the soil system and the state of the soil resource. And I put up with this figure just to help everybody kind of appreciate how not very common soil is actually in the Earth system, right? Because if you think about the radius of the Earth going from the top of the crust to the core, we're talking about something like 63,000 kilometers, right? Of that, only the very top 1 or 2 meters is what we're talking about is soil. So for all essential purposes, soil exists as a very thin veil that covers the Earth's surface. It's a very thin relative to the radius of the Earth, right? But that really thin layer of loose, unconsolidated material that covers the Earth's surface essentially represents the difference between life and lifelessness in the Earth system. As virtually every living member of any kind of plant or animal community that you can think of on the surface of the soil or on land has to depend on food that grows in soil, or we're eating animals that eat that plant that grow in soil, right? So it's depending on this very rare system, relatively speaking, for our survival and extinction, the difference between survival and extinction of not just human, but pretty much all terrestrial life. Throughout human history, there's been also many examples of how human civilization has been intimately tied to the health of the soil resource. You can go back into the civilizations in the Tigris and Euphrates River in Iraq, maybe if you want, or even many other parts of the world, including the Nile Delta, to find many examples of how degradation of the soil resource led to collapse of, at one point, very powerful civilizations. And also keep in mind that only about 10% of the ice-free land area in the world is actually suitable for agriculture. So when I talk about land degradation and how problematic it is, I want you to appreciate that. I want you to remember these numbers so that we appreciate how important this resource is. So there's a growing movement around the world now that tries to focus on this idea of soil health. And soil health basically is this collection of ideas that are meant to support the continued capacity of soil to function as a living system, and recognize it as a living ecosystem that is key for sustaining the lives of plants, animals, and even us. Right? And if you think about the healthy soil idea and what's behind it, we come across, kind of these ideas that I mentioned of soil being a living and vital ecosystem, but also that its quality and how healthy it is at any given point is key to the ability to support the different types of plants that we want to support our human communities and others, and that we also need to be managing soils so that they're sustainable for future generations. And when we say we need to manage them for not just for now, but also for future generations, we're thinking about factors of not just plant production or supporting plant growth, but also how soil is key for purification and delivery of water for human communities, how soil plays key roles in terms of waste and nutrient recycling, and also the kind of work that I do, for example, of how soil plays key roles in climate regulation, which is going to be the subject of my talk in the next section. And also the fact that soil is has the most abundant and diverse community of living things that we know of anywhere else. So every time soil is degrading, we're now, kind of reaching potentially critical points about the diversity and abundance of living things that are living in soil that keep getting affected every time the soil resource is degraded. Okay, so the main thrust of my talk that I wanted to talk to you, though, about is the effort that I am engaged in quite a bit on the idea behind how soils play key roles in climate regulation, and in particular, how soil plays into the ideas of climate change and climate change mitigation. Just to give you a bit of a background, at this point in human history, a collection of human activities, including burning fossil fuels, deforestation, changing land uses, is releasing something like 9.4 billion metric tons of carbon into the atmosphere every single year. Right? You've all heard of climate change because of these human actions. What I'm not sure you might have heard, though, is the fact that if you compare this number with the rate at which atmospheric concentration of carbon dioxide is growing right now, that's actually they're not two identical numbers. Only half of this carbon that's being released to the atmosphere every year actually gets to stay in the atmosphere and gets to directly contribute to this increasing concentration of greenhouse gases in the atmosphere. And that's because the other half is taken up by land and by the seas. In the processes we recognize as carbon sequestration. And this might be a bit elementary for some of you, but I wanted to make sure we're all on the same page. So how does carbon actually get sequestered? And I'll focus on the soil part of this story here, right? Carbon gets sequestered in soil first after it goes through photosynthesis and is, where plants take up carbon dioxide from the atmosphere to build their bodies, and upon death, their bodies or bodies of those animals that consume them return to soil, right? But this is not just a one-way process though, right? Because there are microorganisms that are continuously cycling carbon in the soil system. And this cycling of carbon plays key roles because that breakdown of the residue or the carbon that came in through photosynthesis allows for nutrients to be released, to be provided for plants and organisms to use as food and energy source. And so during decomposition, some of that carbon gets released back into the atmosphere, but some of it enters what we refer to as the soil carbon pool or the soil carbon bank. And the soil carbon bank obviously grows if there is more carbon coming in than what is getting released, right? So this process then allows for carbon to continuously be coming from the atmosphere. And even as the atmospheric carbon dioxide concentration is increasing, so far the ability of the soil to take up more and more carbon had been increasing. But we're not entirely sure that can keep happening indefinitely. So there's no guarantee that the soil can continue to bail us basically from experiencing the full effect of the CO2 that we keep releasing into the atmosphere. And a big part of it has to do with the fact that the soil gets degraded. But before I do that, I just want to highlight another really important part about soil in terms of carbon sequestration. So people like me spend a lot of time thinking about not just how much carbon's in soil, but also in what form is it in soil. And that is key because if I extend that banking analogy that I made before, where the soil carbon bank grows only if we have more carbon coming in than there is coming out, then you can think about the carbon that's in soil as either carbon that's sitting in a checking account where money is coming in and out kind of on a regular basis, or a savings account that actually continuously can build. And the way to think about this is that, when residues continuously entering the soil system, right? But most residue, especially if you think about plant residue, decomposes roughly on the order of about a year or so, especially if it's left on the soil surface. But if that carbon can make it into the soil system, though, it can last there for up to millennia and sometimes even more. And that's made possible because carbon molecules can either form physical association with soils, or i.e. get entrapped in aggregates like this, the dots representing the carbon, if you remember from my previous slides, or because these carbon compounds can actually form chemical reactions that get them to basically chemically bind to the surface of reactive minerals that I mentioned earlier in soil. And if carbon does find itself in one of these associations, then it can last in soil for really, really long time period. And hence, if you were thinking about it from a climate change mitigation perspective, what you want is for that carbon not to just be fixed by plants, but also to be put into one of these long-term associations, right? Because if it's just in plants, you can think about the fact that at best, maybe it stays in biomass 50 years, maybe 100 years. But if it enters into soil, we're talking about a long-term sequestrations that could last for millennia. So by putting in more and more carbon in soil, we are able to then not just build the balance in a checking account, but rather even, kind of increase a long-term saving account that allows soil to hold on to a lot of carbon and contribute in very meaningful ways to climate change. And I want to highlight this figure so that you can appreciate how important soils are, because If you think about all the carbon that's in the atmosphere, in vegetation, and in soil, soil actually stores way more carbon than either the atmosphere or biomass around the world. In fact, the numbers are that soil stores twice as much carbon as the atmosphere and vegetation combined. A big part of it are in these peatlands, in polar environments or wetlands, but you also have significant amount of carbon relative to plant carbon. There's a lot more in soil in a range of other ecosystem types around the world. So soil is a really important storage of carbon across a broad category of ecosystems. And I want to also highlight the fact that soil, increasing carbon concentration in soil, or making it possible for soils to store a lot more carbon through carbon sequestration, is not just a great strategy from a climate change perspective. Because soils that store a lot of carbon are soils that are healthy, that are able to have a lot of nutrients to support plants. A lot of the soils can hold on to a lot of water. And as a result, are able to support a very healthy ecosystem in general. So there's way more benefits to carbon sequestration from carbon sequestration that can come for just climate. So it's great from a climate mitigation perspective, but it's also great from a perspective of needing, developing or protecting a healthy soil that we also need to provide all the food and other ecosystems functions of soil that I mentioned earlier. And obviously this is becoming critically important with increasing human populations, right? We are having more and more people that need to be fed, but the resource base that we feed the people from is what needs to be protected right now. But protecting that resource base from degradation, or and in this case, if you just think about it from an increasing carbon perspective, which is a good way of thinking about soil health and improving degradation, because soil that has a lot of carbon is soil that's not degraded, right? And so doing so then, promoting increased carbon sequestration allows us to work towards multiple benefits at the same time. Increasing food and nutritional security of the growing human population, but also addressing the climate crisis. But unfortunately, the world's soils are getting degraded. There's been report after report that's been coming out over the last few years in particular that have highlighted that something like half of the world's soils are now seriously degraded to the point where their ability to grow plants and to support life is compromised, which means their ability to sequester more and more carbon to help with climate change mitigation is also getting compromised, right? And this problem is extremely widespread. There's virtually no place that doesn't have highly degraded soils. Some places are experiencing way more severe degradation than others, but pretty much soils around the world are experiencing extreme forms of degradation. But if we really want to figure out a way to continue to provide food for the growing human population and continue to support climate change mitigation and all the other co-benefits that I already mentioned, then the good story is we know what we need to do, right? As a human population, we know that we need to figure out ways to reduce continuously disturbing the soil, to reduce the deforestation that still unfortunately keeps happening, to manage how much chemicals are being added to soil, and basically practice best management practices. In the soil carbon world, there's been a growing recognition of these co-benefits, and there's a global effort right now that started in France called the 4 per mil effort that some of you might have heard of, to basically aims to increase the amount of carbon stored in soil by 0.04% every year. The idea here is that that small increase in carbon every year is enough to help offset a significant portion of the human-caused CO2 release into the atmosphere, but regardless of whether we're able to achieve 0.4% or 4 per mil all the time, everywhere, every little bit of effort that goes in that direction, it still ends up contributing to all these multiple co-benefits that I mentioned before. But of course, if I'm talking about soil and carbon sequestration, I can't end it without mentioning there's a part of the world that's experiencing significant change, where soil carbon reserve is significantly threatened now. And these are the polar environments. And if you remember that bar chart that I showed you of soil and plant carbon distribution, the big brown bar that was, and the last one was peatlands. And a big portion of where you find these peatlands is in Arctic systems, high latitudes, basically. But the problem that we're encountering with high latitudes is that historically, they were able to retain a big portion of the world's soils. In fact, they store about 1/3 of the global soil carbon reserves. All of this accumulated because in the Arctic, for example, when you have a short growing season that plants can photosynthesize, they photosynthesize, obviously, right? You experience all sorts of greening. But then it quickly turns dark and cold, and this litter doesn't decompose efficiently. So over hundreds and thousands of years, it built up a very thick reserve of soil carbon. But now these systems are experiencing warming, which means they're experiencing thawing, draining, desiccation that's associated, and thermal erosion that's associated with these warming and drying of Arctic soils, and which is causing even faster release of carbon dioxide and methane into the atmosphere. That release is bad enough, but unfortunately that's not the end of the story. And it's also fueling a feedback cycle where more warming releases more greenhouse gases into the atmosphere that cause even more warming, and that cause even more thawing, and the cycle keeps going on and on and on, right, in a positive feedback loop. And so unfortunately, the soil carbon is an important part of the story from any kind of climate change mitigation strategy. But if the world keeps going in the direction that we are in this respect, I think we're opening ourselves out for even more problems going forward that we've been facing. Okay. And I want to end this part by saying that I hope what I said is convincing that soil degradation is a major issue around the world, and working towards soil health and improving soil health has so many benefits that it's a win-win all around from multiple strategy perspective. And this is something that a former US president from many decades at this point ago said, right? Which I'm hoping, we keep remembering these lessons that hopefully we've learned over time, that unless we actually protect the soils, if we keep destroying the soils globally, we're looking at basically destroying ourselves in the process. And I don't think that's an understatement, especially considering where we are right now. It's not an understatement anymore. And the last bit that I wanted to tell you all is, so I like science, I engage in science a lot, obviously, but a good part of my time these days is also spent thinking about how do we make STEM workspaces in particular more equitable, more inclusive to women, girls, and underrepresented minoritized scholars, as I mentioned, from underrepresented communities and underserved communities. And I want to start by showing you this, right? These are very familiar pictures for anybody in especially the kind of work that we do, right? Be it laboratory or academic research or education, or even expeditions that look like this, which are, this particular image is from a historic expedition from the US Geological Survey. But these are familiar pictures, right? Our academic institutions were created for people who look like that, and people still are dominated by people who look like that. And in many cases, the underrepresentation that Amy was talking about earlier, for example, is a product of these patriarchal, colonial, in some cases, systems that were created to serve people that look like that. And the byproduct of that is now we have STEM workspaces that are not diverse at all, in particular in fields like ours. But not just diverse because there are no people going into these fields, but also they also tend to be very exclusionary. of people that don't fit that mold, right? Those pictures that I'm showing you. And unfortunately, very little has changed in this topic over the last several decades. There's been study after study that has highlighted that decades of efforts to diversify fields like ours, the geosciences in particular, or in engineering, has had very little effect, especially in diversifying the fields at the professor level, so where people like me sit right now. It's extremely uncommon for me to be in a room like this in a meeting with especially people of color that are maybe more than 2% of the population, right? And look around you even right now. It's always the case. And that's not because there are no girls that look like me that want to go to school, or there are no girls everywhere that want to go to school or to do science. But the spaces were not created for people, and hence it's a little bit, it's been problematic. So I work with a very amazing team of scientists in a project that we call Advanced Geo, which is actually funded really nicely by the US National Science Foundation, and is an effort to empower geoscientists in particular to transform our workplace climate, the culture and the climate in our workplaces that has allowed for this to go on, so that we can think about how do we change it. And I give you some examples here just to highlight how common it is that if women actually make it into academic workspaces, how common it is that they experience harassment. Some of it is sexual harassment, some of it is a little bit different because it has intersectional issues with race and racism being intermingled with harassment. But it occurs in classrooms, it occurs in field work spaces, it occurs in conferences, it occurs everywhere, and it affects progress of women in sciences, it affects their hiring, it affects their retention, success in STEM fields. And so what we're trying to do is have these conversations about why do we have workplaces that look like this. And these conversations are always hard, right? But I think we have to have them so that we be reflective about why do we have workplaces that look like this, workplaces where women feel excluded, where women are continue to be underrepresented even with all this effort that's being spent. And hence, you know, how do we change the way we think about recruitment, retention, and success of women and girls in science? And so if this seems interesting, I'm happy to talk to people later. But we also have a very amazing website with a lot of resources that I want to put up here to share with you all. And I think I'll stop there. And I think we have a few moments for questions?
Yeah, sure.
Okay.